I'm really happy to introduce to HAS again, Dr. Jimmy Newland. Jimmy was really pretty. He's been a member of HAS probably for close to 20 years, and prior to COVID, was very active with his high school astronomy course at Bel Air High School that he taught all the way through from 2008 to 2024. And out of that, we had several of his students uh, come and present to HAS the projects that they were working on as part of Jimmy's kind of an extra curricular or extra credit sort of thing for Jimmy's classes. And for me, back when that was going on, one of the coolest ones that I remember was one of Jimmy's former high school students reached out. He's a professional astronomer now, and he asked Jimmy if some of the students could help him work through data and identify some targets for him. I believe it was for Hubble observations, if I'm not mistaken. But it was really cool that that one of his previous students followed through and became a professional and reached back to work with Jimmy's students. Any rate, I uh, uh, Jimmy since 2024 he's left teaching high school and he's completed his PhD in physics education at U of H. He's currently doing work developing resources for integrating computing and data science into K through 12 courses like astronomy for the Texas Advanced Computing Center through UT Austin. So with that, Jimmy, welcome back, and we'll look forward to your presentation.
Thanks, Don. Before I share my screen, I was remembering bringing that group of research students that former student of mine put together out to the dark site, and you made hot dogs for us. It was really fun. And one of the members of that group is about to graduate with her master's from University of Houston. Go Cougs in analytics, and was actually asking about like, are you still doing astronomy things? So I'm gonna remind her of that, of us coming out to the dark site and having hot dogs and seeing cool stuff. All right, I'm gonna try. Oh, can I take over the
Yep.
screen sharing, Stephen?
Sorry, Jimmy, go for it.
Not a problem. Not a problem. I'm gonna just share my whole desktop. And can I get a thumbs up that we can see my desktop? Okay, great. I'm gonna also try to take the advice of the always excellent Steve Goldberg and make sure my mouse is visible. If not, unmute and tell me, can't see the mouse, what are you pointing at? As a matter of fact, y'all, in general, what I would say is if there's something in the chat that I need to respond to, if y'all would unmute and let me know. But, I'm a member of this club, so you can unmute and talk to me anytime you want. So what I'm going to talk about tonight here, I'll get going. So I don't know when I joined HAS, but the number of events that HAS has been a part of for me is really like the drop off after COVID is really hard for me. And it's one of those things that now that I've left the classroom, telescopes are right over here. I've been in the Discord watching people, someone's building a spectroscope. I got a lot. I'm not retired by any means, but the idea that I can, come out to the dark side with my scope now and actually go to Texas Star Party with all that that means, I'm very excited. So I used to be an astronomy teacher. and I would bringing the students, the Bel Air High School Astronomy Club. I'm wearing their sweatshirt tonight from the last year. They're actually still active, and their president, I'm going to share some results of a research project I'm doing with the president of that club. She's a member of HAS too. She just couldn't be here tonight. She's singing at a choir concert. Otherwise, she would be running this show and Jimmy would be muted. But what's she going to do? So I taught physics, I taught computer science, I taught astronomy. And during that time at University of Houston, the premier Houston-based science education university, I really wanted to take the physics stuff I've been teaching and the comp sci stuff I've been teaching and find out how they mix together. So when I joined the Texas Advanced Computing Center at UT Austin, I worked there remotely. I still live here in Houston. I made that a goal. I do professional development for computer science and research for computer science, but I explained to the folks there, I'm like, hey, I want to continue to look at this stuff. I want to talk a little bit more about TAC and astronomy later on, but we'll get to it. And even though there's a QR code here, I'm going to drop a link in Discord when we are done, and probably put it out on the email list too. Everything I'm about to share with y'all is the kind of stuff that amateur astronomers are really good at. Even though I'm going to bring you stuff that came from like the educational sort of side of things, y'all could do this stuff too. Yeah. All right. Let's see. What I would tell y'all that I would want the club members to know, the C-STAR telescope, there was also a discussion earlier about a C-STAR pair of binoculars, but they were not electronic in any way. It just said pairs with C-STAR. So this era of like, hey, you need a smart telescope for your kids. The idea, and I know Steven's going to like this, the idea of taking your Dobsonian out back and doing the Astronomical League observing list, like that does not get in the way of finding other ways to do amateur astronomy. So what I'm going to talk about tonight, in fact, there might be a way, I might be looking at maybe I'll do an Astronomical League observing program and tie data pieces to them as I go and write it up. That would be a really cool thing to share. I haven't done an Astronomical League list in a while. So Stephen, I may be pushing you to, maybe I'll start with Amelia's intro one again. I haven't done that one in a long time. So what I'm doing over at TAC is I'm trying to figure out how to take the data science thing that is a new and very popular topic. And no, I am not talking about artificial intelligence. That's not what I mean when I use this phrase, data science. What I would tell y'all is that professional astronomy has become a data-driven profession. And so much so that when you go to the American Astronomical Society conferences, you'll see companies there hiring astronomers away to work at banks and for political science firms. Data science and astronomy are very tied together, and I had no trouble when I was an astronomy teacher finding ways to teach astronomical stuff like Kepler's laws or stuff about how stars form using data. And that's what I'm going to share with y'all. So from the perspective of like an amateur astronomer, like where does this sit? So we're going to ask a question here. Our question is, we're going to look at 4 star clusters in the Milky Way, 1 globular cluster and 3 open clusters. We are going to try to figure out how their relative ages, not their exact age, but their ages relative to one another. And so that's here. Let me turn on the laser pointer. Can we see the laser pointer? I know Steve's off camera, so he's giving me a thumbs up. Our question is, which of these 4 clusters is the oldest? Which one is the youngest? That's the question we want to ask, which leads us to, well, what kind of data are we going to need to answer a question about the age, the relative age of star clusters? And I promise y'all I'm going to show you what that would be. And then we're actually going to do a little bit of analysis of a data set, an astronomical data set from an actual astronomical archive. And then we're going to try to answer our question and see if we can figure out which of the 4 is the oldest and which is the youngest. And then, I'm not going to take up what I would really want to do is make sure I get to the research Sarah and I have been doing. But it involves Python and a lot of programming. This doesn't. It involves a web browser and you and the mouse. So this data science process here, the statistical problem solving process, y'all, this is just the scientific method. Ask a question, go get some data, figure out if the data helps you answer your question, and if it does, present on it. So what I would tell y'all is, as I've been doing this education research at TAC, the truth is that biology, chemistry, physics, engineering, and astronomy are essentially data science professions now. So it's what I think is super cool about that is unlike a lot of other fields, astronomy has so many open data sets and so many professional or almost professional astronomers who want to share with us as amateurs, like here are some tools you could use. I argue that AAVSO is one of the most important parts of amateur astronomy, but it's also part of professional astronomy. And this is kind of in that vein, okay? It doesn't have a lot of observing in it, but it's like, can we use data to do some astronomy? So let me show you what I mean. Looking at the call, because I know quite a number of you, I don't know how much everybody knows about introductory astronomy stuff, but I'm going to do this slide anyway. It may be a waste of our time, but I hope not. So I'm trying to prove a point about something in astronomy, a plot that we use in stellar astronomy all the time, and it's got some weird features, but they're not that weird. So what I've got here is a plot I randomly sampled from a list of many, many thousands of people. Maybe it was more like 1 million people. I randomly sampled like 100 heights and weights for Americans, and I plotted them here. And do y'all notice anything weird about this plot? Or what do you notice? Either unmute. Let me get the chat open. I got this. I'm hoping. Show chat. Moving the chat. Cool. Anybody notice anything about this plot? Like, especially on the x-axis? Do you notice anything weird there? It's been a while since we looked at plots.
Yeah, you got a group down in the in the lower left-hand corner,
Yeah.
and and um and a group up in the upper right-hand corner that's separated from the group of data in the center.
Yes, so
So there,
there's this trend, right? I
yep,
think. Don, you agree? And there's
yep,
this weird cluster here and this weird cluster here. But what
yep.
about this? What about the weight getting bigger as it goes to the left? Is that typical for when we do plots?
Oh, I didn't even notice that. I
Weight is
didn't even notice
reversed.
the. Yeah, you got me.
Well, I wasn't trying to trick you. The
No.
point I'm trying to make is that you still made sense of this graph, this plot, even though we did something weird with the weight and it actually increases the other way. So the reason I showed this is I feel like when you're trying and a group of amateur astronomers, this is lower hanging fruit than if it's a group of teachers or students. But there's this plot we're about to talk about that I bet y'all already know. It has a very weird feature that is very similar to this weight thing. The weight gets bigger as you go to the left as opposed to the other direction. But we were still able to get to infer stuff. Like you notice that there's this clump over here, there's this clump over here, but there's a clear relationship. So as the weight seems to get bigger, the height seems to go up, with the exception of like there seem to be some people with big weights but low heights. And over here, there appear to be some people with low weights but big heights. So now, oh, and then one other thing, just to kind of prove the point I'm trying to make, just like astronomers do, the code that I use to make this plot, I made available to everybody. One of the things I've discovered is that astronomers have no trouble taking the code and data that most of the time that they are using and sharing it in a public way. It's not always like, sometimes you got to know how to program to like make sense of things, and that can be annoying, but it's still a part of that like big sense of like, oh, they're asking about it, here's how I did it. So it's really, really common to find like code chunks online. So here's why I did that. I assume, well, let's not assume. Can I get a thumbs up if we know what the Hertzsprung-Russell diagram is? Either on camera or give me a, what do you call it? Oops. On a reaction. There we go. Don knows what I'm talking about. Not everybody though. So, yeah, Joe, I know you know. Here's what I'll tell you all about the Hertzsprung-Russell diagram. We could do a whole talk on just the cool science behind it and its history. If y'all don't already know, Annie Jump Cannon, as one of the most important astronomers ever, came up with the spectral classes that we now use in astronomy, even though, well, the blue ones are over here and the red ones are over here. And she came up with a weird little mnemonic that she wrote in her letter to the Harvard astronomy people. O-B-A, fine girl, kiss me. The red stars are on this end and the blue stars are on that end. So now what I've got in the middle is the Hertzsprung-Russell diagram from a textbook. It's from the OpenStax textbook, by the way. It's free. It's fantastic. I absolutely recommend it. If, however, you're going to take your Dobsonian into your backyard, put a digital camera on it, and take a picture of a star to measure its magnitude, there's a long way between taking a camera on a Dobsonian in my backyard and measuring the magnitude and turning that into something like luminosity or even the spectral class, which is really just another way of saying color, but nonetheless. So the picture in the middle, or that one on the left, that's great, but it's kind of removed from what astronomy is doing with actual data. And what we're going to do tonight is actually use some live data to make, instead of a Hertzsprung-Russell, we're going to make something called a color magnitude diagram, which is essentially the same thing, but it's got a couple of caveats. So I realize I remember when I was 9 and or 10 and I got Astronomy magazine. It was the 80s, right? Yeah. And I learned about the magnitude scale, and it was, or maybe I went to a planetarium first. I don't remember, but when I first learned about the magnitude scale and negative numbers being brighter, I still remember that as being something that was weird for me. I can tell you it's weird for high school students, and it's one of those things that, as an amateur astronomer, you look up and see, a satellite passing over, and you're like, that one's about a negative half a magnitude. Or some of y'all that do AAVSO stuff might be able to walk outside, point at a star, and tell me its magnitude, very accurately. The problem is that from all of us have done this before, and it's not that weird, but the magnitude scale being brighter as negative, that actually gets in the way when we're trying to use it in a scientific sense. So you'll notice on the y-axis over here, the negative magnitudes go up. So, oh, and by the way, this is the absolute magnitude, which we're going to be dealing with in a few minutes. And then on this axis, we have something called color index. But I want to touch on the Hertzsprung-Russell diagram, just in case we have people on the call that have never heard of it before. Enyar Hertzsprung was working with Annie Jump Cannon on trying to make sense of the spectral classes. And if you aren't already familiar, Hertzsprung and Russell actually did this more or less independently before they started talking together. And what I'll tell you is all of the stars along this weird little curvy bit called the main sequence, they're all still fusing hydrogen into helium. So then there's a cluster over here, the red giants, where hydrogen fusion has mostly stopped, and there's other kind of fusions happening. Here we've got the white dwarf stars with essentially no fusion left over. It's also got the red dwarfs. So the point is, in order to figure out for this population of stars that's plotted in this textbook diagram, those are randomly selected. They're spread out all over the galaxy. And we have no sense of their physical context, like where are they? How did they form? All of those kinds of things. We're going to get at that. With our 4 star clusters, we're going to get at the fact that they must be together. But we'll get to some of the specifics about what does it mean to look at a star cluster as opposed to this HR diagram of just random stars. So even the one over here, this color magnitude diagram, these are randomly sampled stars. This is actually from a lab that I did in my class. And these are the stars that are closest. These are the stars that are brightest, and the red ones are the overlap. So I want to talk about the color index because I know when I was doing amateur astronomy, probably when I came back to astronomy in 2006, when I learned about color and magnitude and their relationship, which is the kind of stuff that we talk about often in meetings of ours and in literature we find online. The deal with the color magnitude, this blows me away. If I go outside and I take my digital camera and I put my CCD camera that's meant for astronomy and I put a blue filter over it and I take a picture of, say, Vega with only the blue photons, and then I save that magnitude into my computer as a number, one single number representing how blue the star is. Then I take the blue filter off and I put a green filter on. For those that don't already know, the V filter in the visible, in astronomy, V is actually the green filter, if you haven't heard that before. So I put a green filter on, point it at Vega, take a picture, and I get the magnitude in green. Now, Vega might have the exact same magnitude in red, green, and blue. Maybe, it probably doesn't, for reasons, but there's something amazingly cool that happens if you take the blue magnitude and subtract from it the green magnitude. Don't forget, negative magnitude is brighter. So the negative magnitudes over here, just like with the other version of the HR diagram, the ones that move to the left, that's more negative. So it's brighter in the blue. Brighter in the blue means hotter. Brighter in the blue means hotter. So just like on this side, these are the blue colored stars and these are the red color stars. For a color index, if you have a negative color index, if there's more blue light than green light, that star's got to be hotter than ones over here where there's more green light, or in this case red light, than blue. And this B minus V, that is a single number that can represent the color index of a star, which is a direct analog to its temperature. So on this axis, we got the magnitude. That, again, camera, telescope, take a picture, you can measure the magnitude. Now, getting the absolute magnitude is a little bit trickier, but hold that thought. The other thing, though, is you can measure the blue and the green and the red and do all of that kind of work on your own computer with your own stuff at your house. You could go out to the dark side and do this. So you could generate these data points that you see in this color magnitude diagram without needing really fancy computers or lots and lots of data. But if you're trying to answer our original question, the original question was, sorry, that dialog box was sitting there. The original question was, we've got 4 star clusters. Which one's the oldest? Which one is the youngest? And can we put them in some kind of order? The trick is we can use a color magnitude diagram to do that very thing. And I mean we, all of us. It's the kind of thing I can show y'all how to do. So I'm going to show you what I mean. So our original question, we got 4 star clusters. We want to figure out their relative age. Now we could get very fancy and use Python and add in a model and get a much more accurate sense of their age. But we are going to do this without ever leaving our web browser, and we're not going to write any lines of code, but we're still doing data science. Data science in this context is having a research question or having a question you want to answer that requires data and a computer to arrive at the answer you're looking for. So there's a little bit more to it than that, but there are some nuanced details about filtering and stuff that I'll talk about. But in essence, astronomy is doing that in every kind of area you've heard of in astronomy. They're asking questions that require data that have some kind of computer need so that then they can report back on their results. So I'm going to use, and there are a lot of things I could use, I'm going to use a tool from the Infrared Processing and Analysis Center, I think is what the A stands for, IPAC, which is actually attached to Caltech and partially funded by JPL, and still, as of right now, December 5th, 2025, still funded by NASA. Knock on wood if it's nearby you. And this is what I'll say. The Ursa Viewer tool, I first saw it at a conference and it was not for teachers. And I'm like, what is this? This is so cool. So I worked with one of the astronomers to design an activity, which this is a modified version of that I'm going to show y'all here in just a minute. And it's got some super cool features. Like, I actually argue that you can learn about clusters and how what's the difference between a globular cluster and an open cluster? Where are they in the galaxy? how are they different? This is getting at that. So every time I see the VSIG people talking about getting outside, that visceral feeling of putting your eye to the telescope is like, I mean, I get it. It's compelling. I've been there, standing under a dark sky with the telescope there, hoping the raccoon did not sneak up on you and take your snack away from you. There's like astronomy with your eye to the telescope is amazing. I'm here to tell you that I have found a similar kind of, or, you know, at least related kind of joy. Another way to do amateur astronomy is to actually work with data. And that's the experience I've been having. I have these like, the same kind of like amazing feeling of finding a carbon star that I was having a hard time searching for when I make these color magnitude diagrams, and I'm like, I have a sense of the age of this star cluster, and I didn't even have to do any programming. It's also, you can do it when it's cloudy, when it's full moon, because it's full moon right now. So there's like a lot to say about doing amateur astronomy using data. So I went out of my way to write this so that students who are not very good at math can do this activity. Most of these students that were doing this activity were, you know, they were along for the ride, but they were not amateur astronomers who were like, I think this is really interesting. My argument is, this thing I'm about to share with y'all and some other ones I'm going to link to, amateur astronomers can pick them up and use them just like they are. They're good to go. They are designed with students in mind, and with some just a little bit of background knowledge in astronomy, you can do some extremely cool like data science activities. So there are a few things, like if you're brand new to astronomy and you don't really know right ascension and declination, or maybe you've never tried to do an astronomical league catalog, or you didn't know there was a difference between NGC and the Caldwell catalog. There are some things that can, if you just randomly choose a target, you might get a little tangled up if it's brand new for you. I used this activity as an opportunity to talk to students about those things. Like the NGC catalog, there were also people that looked at it with other telescopes and they gave them other names. And in order to get around that weird confusion, the URSA tool uses something called SIMBAD. And SIMBAD is a tool for every kind of an astronomer, amateur or professional alike, that has all kinds of information about stars, clusters, nebulae, galaxies, anything that isn't a solar system object. And what's in there, like information about where to find them in the night sky, other names they might have been assigned, research papers, and links to actually see them in the night sky. Lots of really cool stuff. And the cool thing about SIMBAD is it's built into URSA. I'm going to show you what I mean in here in a couple of minutes. Now, URSA, y'all, I don't know how to fly an airplane. And if I sat in a Cessna, I'm assuming all of the buttons and knobs and the thing you pull, all of that would throw me. I wouldn't even know the first thing about how to like even start the plane. Sometimes sitting down at a tool like URSA is kind of like, which button do I click? So what I went through making this lesson is I don't know all of the features, but I know the ones that can let you make this color magnitude diagram we're going to do. So yeah, we're going to actually do a demo of it here in a second. I actually opened it to make sure it's still connecting. They are set to do maintenance tonight, but at 9 p.m. Pacific. So hopefully we're still good. So I honestly, if you are wanting to dig into this, it's the kind of thing like, I would want to be comfortable with right ascension declination. I would want to have a sense of what I mean by angular size, like how big is the moon, how big is a star cluster. You don't necessarily have to do astrophotography, but understanding a little bit about how astronomy images work might be helpful. You got to know the magnitude scale, and I still think that's like, it's one of those things that, yeah, I'm in on the joke too, but the magnitude scale is so weird. Like getting negative means brighter. That's still weird. Some stuff about clusters, like the difference between them. And I always made sure my students had worked with some kind of spreadsheet data before we did this activity, like Excel or Google Sheets or something like that, because, you know, it can be a little overwhelming for them. I would also say, if you want a challenge, you could try, I did some filtering for you, meaning I told you some appropriate numbers to help limit some of the values here. I'm going to show you what I mean in a minute. But, you know, if you're the kind of person that wants to go find these on your own, that's absolutely a possibility. So Yeah. And I think it's time to actually do it. There is, by the way, linked here is a YouTube video of me going through this demo I'm about to do. And here's what I'll tell you all about this equation. Like, this is known as the distance modulus. The absolute magnitude equals the apparent magnitude, minus 5, minus quantity 5 minus 5 times log base 10 of 1,000 over the angular size. Now, if you don't know that at all, it will be completely irrelevant, and I'll show you what I mean. Sometimes I feel like people like the mathy stuff. Sometimes I feel like they're like, oh my God. The students certainly reacted with like fear when I threw too much math at them at once. All right, so let's actually do this one. I got it open. Oh, I've already searched for it. I'm going to go to the URSA homepage, and I'm going to click on URSA Viewer. The instructions, there is an activity, by the way, with every one of the instructions right there. Here are the 4 star clusters we're going to look at. 3 of them are open clusters and 1 is a globular cluster. 1 is from the Colander catalog. 1 is, I used the NGC name. You can see that 1 of them is a Messier object, and 1 of them is from a group of open clusters called Malat. They're great. I have looked at Colander 110. I've looked at all 4 of these. Yeah. So these are all like, you could observe these. I also went ahead and put in the angular size. You know, I figured maybe people didn't want to have to track that down. I know the students didn't. And I want to talk about this column right here called parallax range. So I'm going to copy that real quick. These 4 star clusters all formed at places in the galaxy that were completely unrelated to each other. So wherever the stars formed for Colander 110, they were at about the same distance from us. All of those stars in that cluster are about the same distance away. They form from more or less the same material, and they all started forming at around the same time. That is going to be a similar story for all 4 of these clusters, but each of them formed in their own place, at their own distance, and at their own time. So they're not all the same age. They're not necessarily made of the same material. It's mostly hydrogen, yes. But the globular cluster certainly looks very different than the 3 open clusters, for example. Okay, so I'm going to go to the URSA viewer, and I'm going to click Catalogs. And then I'm going to let it load. Please load. Live demo. I'm doing a live demo. If Steve Jobs could do it in the 90s and 2000s, I can do it now. And instead of, by the way, this URSA tool that we're about to use, it's called the Infrared Science Archive, but it's got way more publicly available data than just infrared data. For example, the Gaia data is on here, which we're going to talk about in a minute. The Zwicky Transient Facility data, that's visible. That's not in the infrared, that's in the visible. That is available here. You can see that data from the SOFIA mission, the airplane telescope on board an airplane mission. That is available here. So much stuff. All of the Spitzer data is available here. Lots and lots and lots. So we're going to use Gaia. So if you've never heard of the Gaia mission before, for observational astronomy research, it's probably, well, it's certainly one of the most important missions. It's an all-sky survey. They're actually done collecting new data, but it was an all-sky survey that figured out the distance to and the exact color of billions of stars, and we have access to all of them here, okay? So I picked Gaia. I'm going to go to coordinates, and I'm going to put Colander 110. And I'm going to pick 10 arc minutes. Oops, I put degrees. Did y'all see that, by the way? When I had degrees selected and I typed 10, it colored it red. And they're warning me, they're like, that's not possible. We're not going to search a 10-degree chunk of sky for you. That's way too big. I actually meant 10 arc minutes. And I'm not going to change any other features. I picked Gaia, I put the name. Oh, and I want y'all to notice what it did when I typed the name here. If you put in a star cluster that went by another name, Simbad is in the background checking its notes for you. So it said, oh, I resolved that. Let me zoom in a little bit. I resolved colander. Here's its right ascension. Here's its declination. And they gave it to you in decimal and sexagesimal coordinates. So both are there. And just to let you know that it found it. I'm going to hit search. Sometimes this can take a little while. Hopefully I don't have to sing a song. I'm not afraid to. It didn't take that long. That was pretty good. And I want to talk about what it does here, y'all. I typed in a cluster name, I gave it a size, and I picked a catalog, and it brings back 3 super cool things. First of all, this is an image of Colander 110 taken in the infrared. It's from the 2MASS, another all-sky mission. WISE is also in here. If you've heard of the WISE infrared all-sky mission, that data is also here. So the first thing is it actually gives you like a context of where this object you're searching for is on the sky. And if I zoom out, let it load, it actually will, fill in all the details. That's the first thing, even though for this particular activity, for us, it's cool. It's not necessarily helpful for answering our question, which of the 4 star clusters is oldest and which is youngest. The next thing it brings back is, I don't know if y'all can read that number, but it's 5,000. It's more than 5,000 rows. So for this 10 arc minute chunk of sky, Gaia said, I found these more than 5,000 objects. They may be stars, they may be other things. Here they are. And I want to point a couple of things out. Like, y'all, here's one that says null. We need this parallax column right here. There are lots and lots of columns. The one that we need is right here, parallax. And it's got sometimes the data from the actual Gaia database is actually broken. Like it doesn't have a parallax for this row right here. And here's another one that has a negative parallax. That's not physically meaningful. Parallax is an angle, or it relates to an angle measure, and having a negative value is a way for the Gaia people to be like, oh, that's bad data. So this is where I tell the students to go into this box and paste the range, the smart range. And I'm going to hit enter and let it load. I'm going to make it a little bit bigger if I can. So do y'all see there, what I'm doing is I ask the thing to filter. I'm like, only give me parallaxes. So if the camera is Gaia and I'm the star cluster, there are objects here where my right hand is, they're too close. They're not part of the star cluster. They're closer to the Gaia telescope. And there's some over here on the wall. Oh, by the way, this is not a digital background. During COVID, this is some amateur astronomer sold this on Amazon and I bought it. This is a physical, actual screen. So some of the objects on this list, y'all, some are in the foreground, some are in the background. This filtering technique that you see me doing on the screen, it's a way of zooming in. So we're looking more or less, I mean, we could get better, but I wanted the students to have some noisy data. But you notice that we went from more than 5,000 to just over 1,000 points. And I'm going to zoom back out for a minute. And now that we've done that, we went and asked it for the data, we filtered it. Now the only thing we need is this plot over here. So I'm going to hit that button, and I don't know if y'all can see it because the zoom thing is at the bottom, but right ascension is along the x-axis, the horizontal axis, and declination is along the vertical axis. Well, that won't help us answer the question about the star's age, okay? So I'm going to hit the gear. This plotting tool is very advanced. It's using the stuff in the background for those that know computer science. It's using Plotly, which is a Python library for doing visualizations in data science, and they've got it sort of baked in. So instead of students writing any code, it's doing it automatically. So we talked about the color index earlier. Like, we could go out in the backyard, or you could go to the dark side where you'd have less light pollution and literally measure the color index of a star if you want it. It turns out that the Gaia database already has that in there. So if I type BP_RP, I can say, hey, go get the color index for all 1,200 of those. Go get that for me, please, and put it on the horizontal axis. And for the vertical axis, this is where we need to have it figure out the absolute magnitude. And this is where the equation is helpful. Now, I had already had students doing math by the time we got to this activity. My thought process was, hey, if I'm giving them the equation and all they're doing is copying and pasting, is it possible for the students to still make sense of the question I asked, even though they're not necessarily doing any advanced math? And the answer is yes. So I'm going to paste that in there. So the color index is now on the x-axis. The equation that's going to calculate the absolute magnitude is on the y-axis. I want to show you something important. We're all grown-ups. I would not want a chart with the wrong labels. So if I don't change the labels, by default, it's going to leave x as right ascension, which it's not. It's color index. And it's going to leave y as declination. It's not. It's the absolute magnitude, not the apparent magnitude. And then one other weird but important thing. Since magnitude is backwards and negative numbers should go up the vertical axis, I have to click the button to make it do that. And then I'm going to hit apply. And I'll come back to the plot. I want y'all to check this out. Don earlier noticed, and I know I'm using a different kind of pointer, but y'all can surely see the blue box popping up as I scroll. This is the main sequence. Way up here, these are the red giants. Down here, they're white dwarf stars. This is not, I want to, like, this is the thing, when from the like amateur astronomer brain looking at this, I'm like, this isn't from a textbook. I made this. I told the database to give me data about stars. This is a color magnitude diagram for colander 110 that I just produced. I made it right now. So, and I can, with that tool, I can absolutely answer our question. I'm going to do one more thing because I think it's an interesting feature. I'm going to go to the color map and I'm going to type parallax. This is the kind of stuff that data science people like to do. And I'm going to choose rainbow. And I want to show you what I just did. I colored the points. Oops, zoom in too much. I colored the points by parallax. Parallax is an analog for distance, y'all. Color index is an analog for temperature. That means parallax is, well, now we need to know that parallax is an analog for distance. So what's going on here is you can see there's some blue, there's a line of kind of blue stars, there's a line of yellow ones. The truth is that the star cluster is not literally all in one place, it's spread out over light years. So maybe, I don't know the exact spread out, but it's probably light years. It's got a few at least. And what's going on here is what we're looking at is the parallax differences between populations within the star cluster. So that's a kind of a neat, like, extra feature. Here's the like better version of it. And what I want to show y'all, because I really want to get to Sarah's research, what I want to show y'all is this slide. I made a color magnitude diagram for the 4 star clusters. And I want to know, can anybody tell me which one do they think is the oldest? There is a feature on each of these that will give away its relative age. And if anybody knows what it is, I would love for you to tell me. What from these diagrams can I use to get a relative age? It's in my note.
Just how far it goes to the upper left?
Say that again, Joe.
Just how much it goes up to the upper left?
How much it goes to the upper left? Bam, boom,
Yeah.
bing. Absolutely. So
Actually, the turnoff point.
That's the word I was
where
looking.
This point is, where that point is, where it turns off.
Yep. So if you notice in this one over here, NGC 4755, Don, you see the turnoff point is really high, yes?
Yep.
And here we see the turnoff point is very, very low, right? By comparison. Yeah, the one Messier 13, I mean, down here on the bottom left. So which one is older, Messier 13 or NGC 4755? Did I know?
Yeah.
M13 is older. Now,
Absolutely.
Here's what I'll say. If you know anything about amateur astronomy, you know globular clusters are really old.
Yeah.
That's why I threw one in here. So it clearly stands out. I also think that NGC 4755 clearly stands out as the youngest among these 4. I feel like those differences really demonstrated like why this is useful. But if you look at Malat 71 and Colander 110, I purposefully picked ones where it was a little bit harder. Because it's, you know, my personal opinion is the Colander one seems to have a higher turnoff. So I think it's a little younger. And the Malat 71 is a little lower. But the truth is that what we've done is we've taken a data set, we've done a plot, and we've answered our question just using these tools without actually doing any coding. Okay? And I want to get to the next part because I want to let y'all ask me questions. I do want to say a couple of other things. I've got a version of this activity that y'all could work through. Here's the Gaia one, linked at the top. There's another one that uses the Sloan Digital Sky Survey. That's also on the URSA servers. Sloan is a visible survey, y'all, completely available for us to use. The Digital Sky Survey from Palomar, that's on the URSA server. So there's visual photometry available for us to go like do stuff with. I also have an activity here where I had students use robotic telescopes and then they threw it into URSA and then they did found the catalog, overlaid a catalog on it so they could see the targets. I know one of the things I see people talking about sometimes on the astrophotography Discord channel is using photometry.net. You upload a FITS file and it will like give you the sky coordinates. I was essentially doing the same thing, but instead of doing it with software we downloaded or images we downloaded, I used URSA only. So I am not a very good astrophotographer, but I taught the students about how astronomical images are made, and I actually used URSA to do it because I could do it in a web browser. There are lots of other cool tools. This one was, and you can see some of the really cool pictures that we used, and I went out of my way to pick targets that were in the infrared. So when I had them doing that astronomical imaging activity, those were all objects, well, most of them were objects that you really can't see very well unless you're looking in the infrared. My favorite, by the way, is Zeta Ophiuchi down here, which if you look in the visible part of the spectrum, you see the star only. If you look in the infrared, you can actually see the gas cloud. Anyway, not the point. I was able to do this, by the way, because I worked with Louisa Riebel, who actually is one of the scientists and an education person at URSA, and she works for Caltech, and she has so many tutorials on how to use URSA. I've learned it all from watching her YouTube videos. That's the second link there. The top link is to a bunch of other kind of astronomy programs where you might be able to use data. And the bottom link is to some other activities that teachers have put together. My attitude is, y'all are smart enough to pick up these activities and run with them and do, really cool stuff with these activities because you've got the passion and the background knowledge about astronomy. Cool. I promise to leave time for questions, but if I don't talk about Sarah's research, she's going to crawl through this Zoom camera and murder me. So I'm not going to invest too much time, but I will tell you this. Sarah, the first author on this slide, Sarah is a member of HAS. She's a senior at Bel Air. And she's become really interested in astronomy, y'all, because of the astronomy class at school. And leaning into teenagers loving astronomy is one of the things, now that I'm here in front of y'all, and I know I haven't been to a meeting in a while, like there are students out there who would love to be part of what we're doing. We just got to find them, maybe meet them where they are. So, having Sarah as a member who actually did this research with me is super, super cool. So what happened is I left Bel Air and I told Louisa, the scientist at Caltech, I'm like, hey, do you have a data set that I can work on with a student? And she said, yeah. I looked at a chunk of Cepheus, and the data that we collected is all in the infrared, and it needs to be updated, and I think I would like for you to write a Python program to edit it. The code she had written was in a different language. So I'm like, okay, I'll do that. And I asked this kid to join me in this journey, and at first there was a lot of physics for her to learn. She was really good at coding, but there was a lot of physics and a lot of astronomy and certainly research methodology. Like, she made this image. She took our catalog, uploaded it to URSA, made this 3-color image in the infrared. All of the circles you see, those are the young stellar objects that I'm going to show you how we analyzed here in a minute. I'm just like, to say that I'm proud of the work Sarah has done is an understatement. And just to prove like how serious we are about this, we are presenting this science research at the American Astronomical Society in January. So she and her parents are going to Phoenix. I'm going to go to Phoenix. We're going to present our results and then share the data back with Dr. Rebold to do with what she wants. So I'm not going to, let's not get too far into this because I'm nearly at a time when I want to stop. But stars form by collapsing, and as they do, they spin, and a disk forms around them. And I bet this is nothing new to y'all. What we're going to do here is what Sarah and I did is we analyzed the disks around the stars. Not the stars, but the disks around the stars. So if you take all the data, all the like wavelengths available from a star and plot them, and you get a spectrum. By the way, if you don't already know it, we've got members working on making their own spectroscopes for amateur use. And it's super, super cool. So, if you're not on the Discord server, y'all, it may sound nerdy, but there's some great amateur astronomy going on over there. So find your way there. If you point a spectroscope at a star, you get these really well-known curves, sometimes known as a black body. But if you point your telescope at a young stellar object, we can't do a spectrum. We have to do something else. We have to manually build it. And it's a pretty complicated process. It's something known as a spectral energy distribution. So here's the thing. They come in 4 classes. That's all right. You do what you need to do. Love it. You know what? I got to sign off too. As a matter of fact, you know what? I'm gonna skip to the money shot. What I want to show y'all, Sarah and I wrote a bunch of code. I want to let people ask me questions. And we produced these SEDs, and on top of that, our code put them in classes. And so what we did was, without looking at Dr. Rebold's results, we ran it with our code, with our science standards, before we checked with her, and then we compared them. And where we are right now is we have done our science. Now we're giving it back to Dr. Rebold to see if she agrees with what we've done. How many class 1s and class 2s. And the classes, by the way, are how far developed these stars are. Like how far, when a star starts out as a giant cloud and it spins, the disk flattens and eventually disappears. Often it's going to form planets. That's also a super cool thing. But what young stellar objects are doing for astronomy is trying to fill in the gap between a star forming, a gas cloud, and the final star that's just there. Like how do we study it in the in-between states? And without using radio light, you can actually use infrared light to figure this out. So this is like, the results are pretty cool. When I saw that our numbers, like in some class, like the class 2s, there's definitely a weird wonkiness there. But our science matches what Louisa Rebold was doing, and I'm feeling really good about that because neither one of us are professional astronomers. I'm a schmo who loves amateur astronomy, and she's a 17-year-old kid who didn't know anything about physics or astronomy before we started this. And it feels like a huge win to be able to go to the AAS with the pros and say, like, look what we did. So this is the exact same kind of data that I was talking about in the other project, but this one just involved a lot more programming. So the truth is, I feel like the earlier part of the talk is probably more helpful for amateurs. This is kind of advanced. I'm going to stop. As a matter of fact, I'm going to stop right there and let y'all ask me some questions. I know what it's like to be at one of these meetings, and it's like, I wish you'd shut up. I want to go. So I'm going to let y'all ask me some questions. I am going to take this opportunity to tell you how cool the supercomputers are at TAC. And if you ever are up at Pickle Research Campus, you should definitely stop by. We do a lot of astronomy at TAC. I did not know that when I joined. But we do a lot of astronomy at TAC. So it's a super cool place to work. Now, what questions do y'all have for me? If any. I'm going to put my Venmo up here. I'm just kidding. That's actually the same QR code. It's not my Venmo. I'm kidding.
So basically, Iris is. I mean, it sounds like it's very a very broad tool. Is that Is
Yes,
that correct? Uh,
it's a
Um,
very broad tool.
and are there a couple of are there resources there on the Iris what I Ursa I said Iris Ursa website that kind of walk you through some of the capabilities of it?
There are in the slide that I linked right here, there's an entire set of tutorials on not
Okay,
just like, and it's about the science behind Ursa, but it's on how to use them too. Now here's what I'll say though. The people at Ursa, they don't care that Luisa Rebel makes these videos. By the way, Luisa came and spoke at an HAS back in like 2017.
hmm.
I would love to ask her to come talk again. But yes, Don, there's lots of resources on that page to like get you up to speed on how to use these tools.
Okay,
And you know what? Since we are a community of practice, here's what I would say. If other people in the club are interested in like, hey, what can this do? I'm totally down to talk. Like, get on Discord, let's talk about it. And we could figure out ways to use Ursa to do amateur astronomy. I'm on board.
okay. I mean that's a that's a good possibility. Maybe we set up an Ursa channel on the Discord server. You know,
Or some kind of thing. But yeah, that's not
something
bad.
like that.
Yeah.
So.
Other questions, y'all? Or thoughts? Or feedback? It's cloudy, so there's nothing to go do outside. And it's full moon anyway. Well, it's not quite full, but it's bright. Is it supposed to clear up this week?
Yes,
Okay.
starting tomorrow, at least I'm out in the hill country, so it's I get a little before Houston
Yeah,
does, but
send that those clouds, the clear skies, please, Don.
it should.
Great.
Um,
I got a question regarding Discord. Who's working on building some of the spectrometry equipment out there in particular? Who should I go looking
The
for?
channel is called, hang on, I don't want to open it on here. The channel is called Amateur Telescope Making. It's in the Astro Gear group, and Bob Frenzel is the person who has got all of this cool stuff going on. Like, it blows my mind. So cool. Head over there.
Okay. My dad used to build telescopes. He's no longer with us, but I think he preferred building them as to buying them. It just was, he
I get
really
it.
liked that kind of stuff. Yeah, and I'm a chemist, so spectrometry and all that is right up my alley. So it's kind of interesting. I'll have to really look into that.
um, Dawn, just a quick comment about that.
Okay.
There are a couple of commercial versions of spectrographs out there for amateur astronomers, and there's
Okay.
also a kit that I'm aware of that's all 3D printed
Yeah.
and
Okay.
that you
That's
can assemble. And from what I've heard, I've not used it myself, but it's a pretty awesome piece of kit.
Okay. I'm also somebody who has the Synesian. I see colors with letters and numbers.
Okay.
interesting.
It's even more fun for me. It's not even worth actually trying to describe to people if you don't have it or you're not familiar with somebody else who has it. But yeah, it's a good thing for me to work with. Thank you very much for that information.
So in the chat, Stephen asked, are there other big data sets of note we might consider using? There, my go-to is Ursa, but there's also something called NOIR Lab, which is also publicly available data that the trick is it doesn't have as cool of an interface. Instead of having a web interface, you got to like download the data and bring it into your own tool. But I'll tell you what I'll do, Stephen. I will like try to compile some and maybe send that out on the listserv or drop it in Discord. The Noir server and Ursa are my two go-tos. I also personally use Hubble, but I have to use Python to go grab them. So I don't. It's pretty hard to use the web interface for Hubble. Anybody else? Other thoughts? I'm going to stop sharing because I want to make sure everybody can see my super cool, where am I?
Yeah, there you
Astronomy
go.
Club sweatshirt from Bel
Yep,
Air that they made.
very
The
good.
students designed this. I only get to
All right.
wear a sweatshirt 5 or 6 days a year in Houston, so what a perfect opportunity.
Well, sounds like you've landed in a pretty good spot, Jimmy, as far as working at TCCA. So,
Yeah,
uh,
and the truth is I'm kind of eager to get back into HAS. I was also in grad school, so that was
yeah,
part of the deal. And not being in the classroom, you know, so I'm eager to. I haven't been to the dark side in a long time. I'm eager to do more stuff. So y'all want to do this stuff? Let me know. I'm here. I'm a long term member. I'd love to get more involved in this kind of stuff. So let me know.
very good. All right. Well, if there's any more questions, and I agree with Don. Thank you for a very interesting presentation, Jimmy. It's a good starting point. It's kind of like now you've challenged us, right?
Good.
Now we got to kind of dig in and get into some of the details a little bit, kind of
Yeah.
figure it out. All right, great. Thank you.
Thank you very much, Jimmy. And so hope to see you guys next month. Quick note, you'll see here we've got the meeting scheduled for a week later than the first Friday of the month because because of the holiday. But we recently, just very recently, found out that we may not be able to do that date either in person at HCC. So please stay tuned to our website and other means of communication. As soon as we have a finalized situation for the January meeting, we will let everyone know. We're definitely still hoping to have it in person for sure. I don't want to lose a week started in November, but there are some scheduling issues there. So please stay tuned. Be sure to visit us on all of our social media. And if you need any info on getting a hold of us through any of that, just be sure to email info@astronomyhouston.org. So with that, I will say good evening to all of you and clear skies.